Welcome to this video on calculating the electric potential from the electric field. And our goal in this video is to come up with a relationship between V, or voltage, electric potential, and the electric field. And we're going to do so through an integral definition that we can use in multiple situations. Now, what we're going to start with seems to be disconnected from this idea, but I promise you we will get to this relationship as we go. And I want to start here in this uniform electric field where I am going to place a positive test charge, and I want to move this positive test charge from location A to location B within the field. Now we can see here that because it's a positive charge and we're trying to displace it against the field lines, the field will be doing negative work on this charge, or we will need external work to achieve this. But let's look at it from the perspective of the field. So the first thing we want to note here is that when we're trying to calculate the amount of work done to move this positive test charge of value Q, let's say, from A to B, we need to calculate the amount of force exerted here, electrostatic force, times the displacement. Now this is a dot product, remember, and a dot product requires that we only calculate the product between the two components of the vectors that lay on top of one another. And so what we're going to say here is that the electrostatic force, Fe, which we can also write as QE, to put it in terms of the electric field, which ultimately is what we're trying to do here, the displacement is actually going to be in the negative x direction. And I guess I should go ahead and just put here positive x, and this way we'll do negative x just to follow some sort of coordinate system. So if I draw this little diagram here and I'll say delta x is a negative value and f is a positive value, or rather, which would be the better thing to do, would be to say that there's 180 degrees between the two vectors. So really what I'm writing here is QE dot delta x, and being a little bit redundant here, but just to really hammer this point home as to why this is going to come out to be negative. The cosine of the angle here, of course, is going to be 180 degrees. The cosine of that is -1. And so the work value comes out as negative QE delta x in this situation. So this is the work done by the field moving from A to B, and the force and the displacement are opposite one another, hence the negative sign. Now this video is about potential and field, and right now we have work and field. And so what we're going to do is we're going to define the way that we have so far through the idea of potential energy. Now if you were to move this charged particle from A to B, you would be increasing the potential energy. So delta UE, the electrical potential energy, is going to increase. It's a positive value, and that's going to be true when negative work is done by the field, and we'd rather going to write it in this form like so. Now connecting this to electric potential through electric potential energy, we know that the idea of electric potential is the amount of potential energy exerted per unit of charge. And so if we divide each side here by Q, we see that this quantity over here becomes V, voltage, and this side over here, negative W over Q, is the amount of work exerted per unit of charge to move this particular charge between these 2 points. Now, what I've done here actually, what we really should have done is written delta V between the 2 points. But what I'm going to assume in a lot of cases is that V at infinity, and so I guess I can write that over here, V at infinity is going to be equal to 0 volts or 0 joules per coulomb. So essentially what I can say is, if that's true, and V is the potential at a particular point that I'm trying to determine the potential at, that's going to be equal to negative work over Q, but it's the work done in bringing it from infinity. And so that is implying that because one of the V's here, V final minus V initial, if V initial is 0, then I can just have that V at this particular point that I'm bringing the charge to is equal to the negative work done from infinity over Q. Now, we've listed out over maybe 5 minutes of discussion a relationship that doesn't look like it has anything to do with this. But here's where this will connect. If I go ahead and I substitute this idea back in here, QE delta X, into this equation, we can very clearly see that V and E are going to be in the same equation. But let's make it a little bit more useful for more situations. So how about we say that I have a field, and this field is not constant. So I'm going to make it that the field lines are going to maybe diverge from one another, and so we can see that the field is changing. Now I'm still going to try to figure out if I move something from A to something at B over here, and I can set either one of those equal to 0 if I don't know the potential of both of them. Let's say I want to move this charge maybe like that. Or I could even say I want to move this charge perhaps like this. If you remember, the electric field is a conservative field, so the force exerted are conservative forces which are path independent. So it doesn't actually matter, which path I take, as long as I'm moving between a potential difference, which in this case I have. Now what I'm going to write here is that in order to calculate this, as the field is changing as I work my way from A to B, what I'm going to do is say that at every tiny little piece of path that is traversed, and I'm really only adding up portions that are at least 0 degrees somehow or 180 degrees to the field, I'm going to calculate a tiny amount of work that is going to be done, and this tiny amount of work is going to be done over very tiny ds. You could write dx as well, but I'm going to use, oftentimes for a path, we're going to use s. I'm going to say over tiny little displacements, tiny amounts of work are done. And this, obviously, you can see connects to this idea. Now, we know that if we integrate both sides, we sum up all those little pieces, we get a total amount of work done on this side. And over here on this side, what I can say is that Q, obviously this little positive test charge that I'm moving, has a constant Q, and then I have integral E dot ds. I left the dot out over here. So we have this relationship, and we're going to go from A to B. Now, as it stands again, this is electric field and work, not electric field and potential. So what I'm going to do is come back to this idea over here. If I divide both sides by Q, I'll go ahead and do that. What I'm left with is I can calculate the potential at a particular point, or the potential difference, right? So maybe let's go ahead and start with the potential difference is equal to, and now we have to remember to put this negative back over here. The Q has factored out, and I have negative integral E dot ds. Now, of course, if I'm going from an initial position, which here I've defined as A, but I could make it more generic and say some initial position to some final position. If I make the initial position or the initial potential equal to 0 because that is at infinity, then all I have to write here is just V. V is equal to negative integral E dot ds from one end of the path to the other. And here I have a relationship that connects these two ideas and can be used across multiple fields. In the next very short video, I'm going to take a look at an example of moving a charge in the vicinity of a point charge and look at how we can actually use that to calculate the potential.